section of chapter 6, and we'll just do a little brief start to chapter 7.1 because this is a combined test. We're going to combine assessment. It's going to combine the intervals from chapter 6 with the inference tests that you're going to be doing in chapter 7. But today we're just going to try to set up our null and alternative hypotheses, but that's at the last part of the day. So now we're going to be doing confidence intervals, and it's going to be kind of similar, but we're going to be doing it for population proportions. Now, population proportions are always z-values. Why? Because you basically have its population distribution, which means you know everybody about the population. It's a probability distribution. It's actually a binomial one. Binomial version. And since you know everyone, because you know the distribution, when you did your 1var stats L1, L2 on the calculator, you noticed that there was no sample value. So there is only a population value. So only sigma value for a probability distribution. So that's why you know everybody. So you can be less conservative than we were with T's, and you can use a Z. So the sample proportion p hat is going to be our best point estimate of the population proportion p. So p hat is our best estimate of p. And how do we find p hat? Well, sometimes it'll be given to us. It'll be the sample proportion, unlike the population proportion. But sometimes they'll make us find it, like 10 out of 20 people or something like that. And you'll have to find p hat using your formula. Now, in order to do inference, meaning finding the confidence intervals, doing tests like we'll do in chapter 7, we would need to still have those same conditions, that random, that independent, and our nearly normal condition. But this nearly normal condition is very important to this type of problem to know if we have enough to really fit a population to the probability distribution that we think is true. So it is going to be very important that you do this check on your paper to establish that this problem really can use this process. And as you can see in this formula, I'm using P and Q, which are the population values, but probably if you're doing an interval, you don't have P and Q, you probably only have P hat. So when you don't know P, you can use P hat as your best guess at P. This textbook says that you can use this for normal, to prove normalcy at a level of 5, but that's fairly low, and it's definitely more widely accepted that it's 10. So, and all this is kind of a little bit made up, and if you were here, we could chat about it, but we're going to use 10 for the purposes of the notes, and you'll notice the answer key to the homeworks are attached so you can look at the answers. Okay, critical z-value. So if we're going to find a critical z-value, we need to know what the confidence level is. So you're going to need your confidence level. You'll need to know your alpha so that you can put it into the equation and find your critical z. You're going to find your margin of error. You're going to see that this formula is going to be a little bit different because it's still going to involve that critical z, but since you don't have a standard deviation, you actually have to make that standard deviation using the proportions. and the size. And then you're going to find your confidence interval by taking your mean and adding and subtracting your error just like you did, and then interpret your results in context. And that'll sound really similar to what we did last class. So here are the formulas. Margin of error, you can see that the hats are on the P and the Q. You can see your critical Z. Oh, I forgot my little asterisk on my Z, but you know, big deal. But I'll put a little asterisk there. The textbook doesn't use that, so but I really like to do that to identify that as a critical value. And then notice that the symbols have changed for our confidence interval and our point estimator, because we're not estimating mu anymore, we're estimating P. So instead of mu, we're going to put P in the middle of our confidence interval, but that interval was still generated using sample values. So of course your sample value will be in your interval. It was generated using your sample value. We are trying to get an estimate of our population value, in this case a proportion P. Okay, so we have a random survey of 1,219 U.S. high school students. 354 said that their favorite sport to watch is football. So, and we're going to try to find a 95% confidence interval for these, for the proportion of high school students who say their favorite sport to watch is football. So first of all, the point estimate. The point estimate will be our sample value. And we had 354 out of 1,219. So we got a value of whoops, I've got to punch that in. We got a value of 0.2904. Now we're going to check the normal condition to see if we can proceed. We do not know P. We don't know it. So we're going to use P hat. And so that means we will use the 0.2904, and we will use Q hat, which will be 0.7096. Now, since we had our sample sizes, we actually know that P hat, N times P being greater than or equal to 10, and N times Q being greater than or equal to 10, but we had to use the hats because we didn't have the P and the Q. When you do N times your P hat, when you do 1219 times 0.20 or 2904, you actually end up back to where you started with the 354. And that's definitely greater than or equal to 10. And Q, since Q involves a proportion that's higher than the P, I don't really need to check that. I do see that it meets the nearly normal. Because I have P and Q, my estimates of them anyway, were big enough. Now, if that was not nearly normal, you could stop right now, or you could try to solve it using Chapter 4 binomials, but if it was not nearly normal, you could stop, at least for doing a confidence interval. Okay, critical value. We want a critical value for our Z. It's a 95% confidence interval, so my alpha is 0.05. So I'm going to get my favorite number, which always is the same for Z. They're always the same. T is the one that changes because of your degrees of freedom. Okay, so now I'm going to find my margin of error, and that takes my critical Z value. If I don't want to write the subscript, I don't really have to. But then this formula uses N times, or P hat, let me just write it all out, Q hat over N, and then, so we're going to put in all that stuff into here, and then I think we can punch it into the calculator just to 0.2904, 0.70696, and then S squared, it's there was 1,219 people, and I got to put the square root over the whole thing. So I'm going to punch that in the calculator just because I want to make sure that I don't mess it up. Okay, so I've got my 1.960 times, and then I'm going to take out the square root here. Now when I punch this in, I'm actually going to use more decimal places because I don't want to have rounding errors. 40, and then times, and then I want to do Q, so 0.7095. How about 9898? So I don't have to round that. Let me make sure. 98. Okay, and then divided by. It was 1219. And so then, and then I got to make sure that's all under the square root. And so you might have to close your parenthesis. Shoot, I guess I have to close my parenthesis. Oh, I guess I punched in an extra decimal. Okay, let's see if that's right. Okay, let's try that again. See, things happen. Okay, so I get a number of 0.02548, and that number I am then going to bring down to, that's the margin of error, and I'm going to add that, and I'm going to subtract that from our proportion value. So let me write that number down. Okay, so that was equal to 0.02548, and then to get my confidence interval, I'm going to take my p hat and add it and subtract it from the error, not mu, p hat. So 0.2904, and I need to add and subtract it from my value. And so that gives me a high value of high value was 0.3159, I guess, with rounding. And then my low value is roughly, let's see, negative. And really, I should probably round these to 3 sigs at this point because I used only 4 sigs when I was doing this. I'm going to round it to 3 sigs. Okay, well, barely enough room to fit P in the middle there. So my proportion went from that's not rounding correctly. My proportion went from a 0.265 to a 0.316. So let's write our sentence. With 95% confidence, the interval from 0.265 to 0.316 captures the true proportion of high school students who like watching football, whose favorite activity is watching football, whose favorite sport to watch to watch is football. Football. I don't know if they mean American or European. Well, anyway, now adding a little step here of what is the thinking behind statistics. The thinking behind statistics is we just came up with a window of what we feel may have, and we don't know if it did, but we think it may have caught the true mean of US, I should probably put the word US in there, USA high school students whose favorite sport to watch is football. So then I go and do a survey at North Country, and I see that at North Country, we get 40% of North Country students say that their favorite sport to watch is football. So what do we think about that 0.40 compared to the window? And this time I'll write it with the, I'm going to write it in that looking like a coordinate, but it's not. It's a confidence interval. What do you think when you compare these two things together? Use numbers. So I'm going to write, since 0.40 is not in the interval, and I need to say the numbers from 0.265 to 0.316, what would you think? Do you feel like North Country kids are like US kids, or do you feel like North Country kids are different from USA high school kids? I would say, since this is not in the interval from I believe that NCUHS students are different from whom? From whom? I don't know. Whom? From USA high school students. That's the idea. If it was in the interval, then I wouldn't think of us as being different. I wouldn't have evidence of us being different. Maybe we still are. I mean, we're pretty cool. So we could be, we definitely could be different. We don't know if we're the same. But so that would be the conclusion I would draw. Because the 0.4 was not in the interval of 0.265 to 0.316, I would believe that North Country students were different than other USA high school students, in regards to watching football, in their preference of liking football. Forgot the context there. Okay. All right, let's do another problem. So, simple random sample of 900 US adults was asked who are the most dangerous drivers. The results were 63% said teenagers, 33% said people over 75, and 4% had no opinion. I'm happy to say I was not in any of those groups. All right, let's find the 90% confidence interval for the proportion of US adults who think teenagers are the most dangerous drivers. So we're going to do all the steps. So the first thing to do is to identify our p-hat. And since we're looking for people thinking that teenagers are dangerous drivers, we are going to use the p-hat of 0.63, which was the dangerous drivers, which means my Q hat is everyone else, is the 1 minus 0.63. So it's putting all those other people together, so 0.37. So that's my estimate of my P. And now in order to see if I can even do this problem, I should check n times p if it's greater than 10 and n times q being greater than or equal to 10. Don't skip this step because you might have a chance sometimes to not have to do the problem, and that would be nice. And it definitely is not nice doing a problem when you shouldn't. So there's the P, which won't be the controlling check. The controlling check actually will be by the Q. Now notice I used my P hat and my Q hat because I did not have the population values. Well, it's not your lucky day. It's nearly normal, so we will have to do this problem. Okay, and then of course this problem would still need to be random and it would still need to be independent to be done. Okay, so then the next step on our list of things we had to do was to find our critical z value, because remember, these are always z's, so we're going to find our critical z value. Okay, so, and what level are we doing this at? We're doing this at 90%. So 90%, which gives us an alpha of 10%. And so then I'm going to have to punch that in. Why do I not have my answer? So inverse normal of a 0.05, left tail. I get my critical z for a 0.10 over 2 is 1.645. Okay, so now I've got that. Now I need to find my error. So now I'm going to get my error. My error will be my critical z. And then remember, this isn't means, this is proportions. So I have to use the proportions times each other. I need to have the sample size. So I'm going to punch those into my error formula, 1.645. And then my p, which was 0.37 over the square root of 900. So let's see, times square root. I get, and I used the answer key on my calculator just now, so I'm probably going to have pretty good decimals. And that's my error, which I then bring down to the next step, which is taking my p hat and adding and subtracting my error. So if I do that, I'm going to have my p hat of 0.63, and I'm going to add the error of 0.02647, and I have 0.63, and I'm going to subtract, I'm going to keep some more decimals, 0.02647, so just because I have them. Okay, so let's say add my proportion. Okay, 0.604 with rounding, and then I'm going to subtract that. And I get 6. Okay, so there's my window. Notice I put a P, not a mu, in the middle. So with 90% confidence, the interval from 0.604 to 0.656 captures the true proportion of, is this adults or is this, who was asked? U.S. adults were asked. Of U.S. adults who believe teens are dangerous, the most dangerous driver. Teens. Dangerous drivers. But, that's not good for you guys. You guys are teens, so you don't want that to be true. So I have hired this public relations campaign. I am paying them big bucks, people, to change the minds of adults about teenage drivers. I have had it with them thinking you guys are hell on wheels. We are going to fix that. So I paid big bucks to this public relations campaign, and they did their campaign. And after the campaign, somebody went out and took a new sample, brand new. And this time they got 0.61 of adults feel that teens are the most dangerous drivers. Is this campaign working to lower the proportion? Now, someone who doesn't know statistics might say, yes, 0.61 is less than 0.63. 0.61 is less than 0.63. But, and this part you don't really have to write on your thing, but is it statistically less? Boy, my rating's really getting bad. Okay, is it really less? No, it is not, because when I look at that interval, since 0.61 is in the interval, then statistically speaking, it is not different from a 0.63. It does not appear to be changing the way the US adults believe, because just by chance variation, I would expect values to appear in my window. And so we don't know what the true proportion is, but that number is not different enough. So here's the way I would word my answer. So here's my answer to the question posed above. Is the campaign working? My answer is, because I'm going to start with the numbers so that you know why I'm going to say what I'm going to say. Because 0.61 is in the interval from 0.604 to 0.656, I don't believe the PR company is lowering the proportion of people who think teens are the most dangerous drivers. Lowing, that's, okay, that's kind of funny. Oops, LTS. Who think teens are dangerous drivers. Most dangerous drivers. Okay, and there we have it. So that's the idea. So you're going to have to draw a conclusion on your mini quiz. Do you believe that there's evidence that there's been a change or not? Does not appear to be evidence of a change. Maybe they have done it, but I don't feel like it's different enough that I will agree with them and believe that they really did. All right, so then that kind of leads us into the next thing, which is going to be, that's the end of chapter 6. Those were confidence intervals. And then the other type of inference that we'll be working on would be a hypothesis test. So what's nice about an interval is it gives you a window of reasonable values. What a hypothesis test does is it takes a sample value and compares it to a hypothesized, what you believe, population value, sample value to the population value, and tells you if that population value really was true, what's the probability that you got the result that you got. So, it doesn't give you quite as much information about the window of potential values, but it compares a sample value to a value that you think might be true and looks for what probability of that happening is. If the probability of that happening is really low, that's giving you evidence that you are not going to believe the population value, that you think there's some other alternative idea of what's going on. So today we're just going to set up the hypothesis statements, and we'll just read the problems and see if we can figure out from the problem how we would write our statements. So, for example, we have an automobile manufacturer and they advertise a new hybrid car and they say that it has a mean mileage of 50 miles per gallon. They're saying that the mean is 50 miles per gallon. To test this claim, a sample would be taken, and if the sample mean differs enough from the advertised mean, you would say that the advertisement was wrong. So I would be looking at, they said it was 50. I would be wondering, maybe is it not 50 in this situation? Now, sometimes you can look for, do you want it to be more than 50 because you want to see if it's doing better than they said? Or maybe you're looking to see if it's doing worse than what they said, and that would be less than 50. But if you're just wondering if it's different, then you would use not equal to. So we're going to write some of these tests. And so each statement's going to have, you're going to have a statement or claim about the population, and that will include population parameter symbols like mu or p. You could even write some for sigma or any population symbol. And you're going to need to have a pair of hypotheses. The one that is the claim and the other one's the complement. We always assume the null hypothesis is true at the beginning. So we're always going to have the symbol of equality being in our null hypothesis, the being equal. We are going to be looking for evidence of it being not true and rejecting what that null hypothesis said. So the null hypothesis is a statistical hypothesis that contains statements of equality like less than or equal to, or greater than or equal to. I like to use equal, and that's a more current way to do it. This textbook uses all three. To test the null hypothesis, we either fail to reject or reject the hypotheses, and you can never accept your null hypothesis. Just think how in the courtroom when they say that you're not guilty, they never say he's innocent or she's innocent, do they? They say not guilty. So our entire judicial system is actually based on null and alternative hypotheses. Okay, alternative hypothesis will be a statement of inequality, such as greater than, not equal to, or less than. If it must be true if the null is false, and we say H sub A, that's one way to say that, or alternative hypotheses. So here are some hypotheses. This would be if you thought there was a difference. This next one would be if you thought that you were looking for evidence of it being lower, evidence of being greater, using symbols of mu. Same concept, but using symbols of P for proportion. Those are the two that we'll be using for our hypotheses. So the next page, we're going to read the sentence, see if we can figure out what the sentence is saying in math symbols, and then write our two hypotheses. Okay, we'll see if we can figure out what they're saying, what we're testing. We always test, the test claim is always a null. Okay, so when the gas pump at ABC says 1 gallon, the gas delivered is actually less than 1 gallon. So gas less than 1 gallon, gallon being units, I'm going to be using mean symbols. From the statement, I see this statement in the problem with a no equal sign. Okay, here's my null, here's my alternative. I'm using a colon, not an equal sign, that's a colon, 2 dots. Okay, the null is always equal. In the textbook, they would have written the null as being greater than or equal to 1 gallon because they would have looked for the complement of the situation. So complement. But okay, so we know the null is always equal, and that's always what we're going to test. And because there is a there's no equal sign, no equal here, that will be our alternative. So less than 1. Whoops, why did I write a 0 there? Sorry. Okay, so we're going to think it's 1 gallon until we find evidence that it's less than 1 gallon. And we're testing, we think it's equal to 1 gallon, but they claimed, or this is the claim, is that we think that it's less than 1 gallon. Actually, I guess they claimed yeah, we were testing a claim of that. And this isn't a big deal. It's just for the homework they do ask about that, but I'm not going to ask for that on any quizzes or tests. Okay, H sub O, H sub A. Okay, decide what symbol. Are you going to use mu or are you going to use P? Mean height. Mean height is 68. That's the null because there's an equal sign in it. Inches, I'll just put the inches there. So did they ask us to be greater than, less than, or different? And since they didn't say anything in there, then I need both sides. I need to look at being different. We always test the null. And this was what I read in my, when I say claim, it's like what's the wording of inequality or equality that I see in the sentence. Okay. Null, alternative. Greater than half of internet users are women. Is that a mean or is that a proportion? That is a proportion. The proportion greater than half, 0.5. Do we see an equal sign on that? No. Do not see an equal sign on that, so it will be my alternative. Now the textbook would have written the null as being less than or equal to 0.5, but we're just going to use an equal sign. So P equals 0.5, and the claim that was in the sentence was greater than 0.5. But I always test the null, always test the null. Okay, at least. So is at least 40%? Is that means or is that proportions? And what does at least 40 mean? If I say bring at least $40, you would be okay if you brought $40. So when I think of the proportion and I'm trying to decide, is it this or is it testing the second version greater than or equal to? At least means you need that or more. So that is going to be the greater than or equal to. So my null and my alternative, P is going to be greater than or equal to 0.40. P is going to be less than 0.40. Now that's fine, and that's what the textbook would say. As I said, you can just use an equal sign here every single time, and then you never go wrong with that. So test the null always, and which one was in our sentence? It actually was the, this one being the null, they actually had claimed at least, so that was the claim. Okay, mean SAT score, well, they're telling us it's a mean, so when you're deciding between mu or p, I'm going to go with mean, and so I'm going to use that symbol, using my population symbol to write my hypotheses. I know that has to be an equal sign, and let's see, the mean score last year was 1,538, so they said it is this. So I'm going to test it not being that, not that. So that's not that, which means not equal to. So not equal to and 1,538. But what was the sentence claiming? The top one. And they still will always test the null. So you can just write test on the null every single time and you'd never be wrong. So now you've got 2 mini quizzes to try, the second one being just writing your null and alternative hypothesis, because we'll find out what problems you're having with that right away before we actually do the test next class.